Okay, where do we get going here? Just for those of you that don't know the drill is I'll introduce Kurt, and then he's gonna give a talk for about 35 minutes or so. If he's nervous, it might be faster. If he's calm, it might be slower. And then we'll open the floor up for questions, and we'll try to do our best on Zoom. It's not the easiest thing in the world. There is a little raise your hand thing in Zoom that you might be able to find. So Kurt and I will try to manage that as best we can. And then everyone except the committee and Kurt will leave the Zoom, and then we'll ask Kurt a few more questions, and then Kurt, you'll have to get off and the committee will confer, and then I'll text you to have you come back in and we'll talk to you. Okay, so it's my pleasure to introduce Kurt's PhD project here. So Kurt got a bachelor's in chemistry from here a while ago, 1990, that double majored in Japanese studies. So Kurt is sort of a Renaissance guy. Then he went down to Institute of Paper Science and Technology and got a degree in paper science in 98. And then he had various industry jobs. He worked for James River. He worked for the Kimberly-Clark pulp mill in Everett. He was a mill manager. He was also on the paper side, which was super good for us when we hired him here because we have pulping and paper making downstairs. He had some other jobs after KC, and he started here. We were lucky enough to get him here. Started in 2015, where he runs our paper center, and he also is heavily teaching with Anthony Renata in the 2 laboratory classes that we have in the curriculum. And I just want to say a little bit about this project because it has been pretty interesting. It's kind of how research goes here. So Kurt was interested in doing something with hop bines, and I think this is his, so affinity to beer it was a real connection for the whole thing there. But he wanted, and this is the bine that the hops go on in Yakima, and he was interested in that as a fiber source for making paper. But when he looked into it for the supply, it's once a year, and he looked into environmental stuff quite a bit in the life cycle assessment, and he concluded that there's nanocellulose that he's going to talk about there, which would be a much better product to produce from hop bines than trying to make a pulp fiber. And then when he got into looking at making nanocellulose, what he found out is that the current processes for making that weren't particularly commercially viable. In fact, they're pretty lousy in general. And so he launched into this other track to figure out how to make the nanocellulose. And that's most of what he's going to be talking about today. But you'll see he did get back to the hop bines in the end and showed that his process does indeed work with that raw material too, which is great because he showed that we can use a variety of feedstocks for his process. And so he's come up with this really nice process. It has a lot of potential, I think, going forward. So Kurt, I'll just turn it over to you, and you can, show them what you got.
All right. Well, good afternoon, and I want to say thank you to everybody for honoring me with your attendance and your support. The title of my dissertation is Nanocellulose Design, Characterizing Ammonium Persulfate Oxidation of Wood and Non-Wood Agricultural Residuals. So I'll first speak to the relevance of my work. I'm going to guide you through my research problem, and then I'll summarize my solution as I've compiled it in my dissertation. So first, I want to establish a little bit of a context and relevance for this work. Plastics are one of the single largest contributors to pollution of our oceans, and continued use of plastics, I think everybody would agree, is not sustainable. 500 million tons of plastic are produced annually, and about 12.6 million finds its way back into our oceans to contribute to that 5,200 billion pieces of plastic that I think we've all seen on TV that are currently in the ocean. But we can change our behavior by turning to the world's most abundant natural polymer, cellulose, or more specifically, the building blocks of cellulose fibers, nanocellulose. In addition, we can source this from natural fiber, such as renewable agricultural residuals. So besides being both sustainable and renewable, nanocellulose has some properties that oil-based polymers simply don't offer. The first being a high tensile strength. It's on the order of the strength of Kevlar, for example. It has a variable aspect ratio, aspect being length and diameter. You can functionalize it depending on your end purpose. It's also biocompatible, and it has some optical transparency properties that are unique. So if you look at this diagram over here on the left, you have a fiber, and fibers are on the order of 5,000 nanometers in diameter, very similar to a human hair, if you want to put it on a relative scale. And when we drill down into the fiber to the first nanoscale building block, we get to what's called microfibrillated cellulose. And it's about 1,000 nanometers, or equivalent to the size of a red blood cell. And just for a frame of reference, the coronavirus is 100 nanometers in diameter. Hepatitis is 50 nanometers in diameter. Nanofibers reside in the 20 to 2 nanometer range, and they can be divided into two categories. We have nanofibrillated cellulose, which retains the amorphous and crystalline regions in the fibers. And then we have crystalline nanocellulose, which the crystalline or the amorphous regions have been removed. So I presented both an environmental and a functional justification for utilizing nanofibers. Looking at the economic prospects for nanofibers reveals several things. First, the nanofibers market is forecast to be $4.4 billion in size. 75% of that is polymers. If we divide that, we can find that natural-based polymers account for 21% of that market, or about $701 million. And then cellulose-based, 69% of that is equivalent to $483 million, or 11% of the entire market. Now, nanofibers have a lot of uses and applications. They can be used in composites, barrier applications, for example, such as packaging and membranes and films, used as a rheology modifier, so coatings and paints, or in transport functions for biomedical. Now, if you look at the breakdown between those two types of nanofibers, you can see that nanofibrillated cellulose is about 57% of the market. Crystalline nanocellulose, or CNCs, are 42%. Then we have this little sliver up here, and that is bacterial-based nanofibers. With regards to the way we produce nanofibers, there are three methods for producing nanofibers: chemical, enzymatic, and through mechanical means. This table summarizes the environmental impact, the energy requirements, and then what that process is capable of developing in nanofibrillated cells. But to produce a nanofiber that helps solve our environmental problem, we really need to have an environmentally friendly method. And of all these methods, enzymatic and mechanical methods are the most environmentally attractive. However, mechanical requires the most energy to accomplish. And unfortunately, both are limited to the upper range of nanomaterials, so microfibrillated cells and down to the largest size nanofibrillated cells. What that means is, in order to get the same physical properties, you have to use more of the fibers compared to nanofibers. Of all the chemical treatments, acid hydrolysis is the only commercially scaled process to date, but it has some limitations. It's limited in the surface chemistry it can develop. It has environmental disadvantages, and it is also one of the higher energy demanding processes. Of all the chemical treatment, or of all those chemical treatments, tempo is the most well documented in literature. Unfortunately, it is the most toxic, and it's not biodegradable. It also has the added limitation of not being tolerant to lignin. But it can develop a wide variety of surface charges, and it gets us down into the nanofibrillate cellulose and crystalline nanocellulose region. Ammonium persulfate, the chemistry I'm targeting, suffers from very poor process documentation in the literature. And it also has some poor perceptions in the literature as far as reproducibility and reliability. But it has several advantages that Tempo does not. First, it's been identified by the United Nations Environmental Program as a biodegradable chemical, and so therefore non-toxic. And it has the added capability of being able to tolerate lignin-containing biomass. So the implications for our process is that we potentially have an opportunity for our spent ammonium persulfate liquor after we've finished with our oxidation, that perhaps we can return some of the sulfur and nitrogen that are left over back as a soil amendment. So regarding economics, I chose to compare the economics of ammonium persulfate to Tempo, as the chemistries are very similar, and what they can achieve from a designer NFC is the same. Using the bulk price for Tempo chemistry and APS, I relativized previously published economics to Washington State mid-sea electricity prices. And in this table here, you can see the relative prices that have been published versus my results. And also I tried to relativize to a similar surface charge development. And you can see that to make 1 kilo of nanofibrillate cellulose using the Tempo method costs nearly in the range of $104 to $107 per kilo, or about 20 times what ammonium persulfate is. In my process, I can produce the same level of surface charge and morphology for about $5.50. So it's about a 95% cost savings versus Tempo. So the main focus of my PhD research is to develop a green method for producing customized nanofibrillated cellulose fibers from either wood fibers or agricultural fiber residuals. I've divided my work into 2 parts. In the first part, I examined the oxidation of cellulosic biomass using ammonium persulfate. I characterized the fiber response to varying treatment levels using response surface methodology. And then I applied that response surface methodology to lignin-containing agricultural residuals. So I'll first present the methods used and then a discussion of the results. So ammonium persulfate chemistry is pretty interesting. It's activated by heat, and once activated, it very rapidly dissociates into its reactive ions, the first being the sulfate-free radical. And so if you look at this diagram, the first reactions that start to occur are hydrolysis reactions that reduce the diameter of the fibers, and at the same time convert the surface hydroxyls to an aldehyde form. As that's progressing, the APS continues to dissociate into a peroxyl radical and sulfate ion. That acts in a number of ways. It converts the aldehyde to carboxylic acid on the surface, and it also begins to start reducing the length of the fibers, as well as digesting the amorphous regions. One thing I think that's really interesting and unique about ammonium persulfate is the hydrogen sulfide ion and peroxyl radical can also form what's called Carrow's acid. And Carrow's acid is a very strong delignifying agent, and maybe what's responsible for why ammonium persulfate can tolerate lignin-containing biomasses, and that's represented here. So in our process to oxidize using ammonium persulfate, it starts with pulped fiber. And we place that in a continuously stirred temperature-controlled reactor, also known as an Erlenmeyer flask in our case. And the reason for that is we wanted to make sure that any potential reactions that could scavenge ammonium persulfate, such as reactions with metals or chloride ions, were controlled and reduced. And if you look at this lower left-hand image here, that's a photograph of the actual reaction and process. Once the reaction goes to completion and we quench it, it requires a purification step, and we do that through dialysis. And here, dialysis takes about 3 to 4 days. We try to get it down to a fairly low conductivity. And the finished product looks like this. It's about 1 to 5 weight percent fibers, still fibrous, which requires a third step of mechanical defiberization. And in our process, we use high pressure microfluidization and or ultrasonication, followed by centrifuging the samples. The resulting samples look like this lower left or lower right picture here. This sample here is high charge, this sample is low charge. So at a constant concentration, as the charge is increased, our colloidal stability improves and the transparency of our product increases. So now I'll summarize the methods used to characterize our process, and I'll quantify the relationships between both the treatment and the responses. The experimental design that we selected is called a central composite design. It has some features that are unique to it. In a central composite design, it's both orthogonal and rotatable, meaning the factors are uncorrelated, and the distance between all the factors and the center point is equal. And what the center point confers is it allows us for detecting systematic drift or changes in our process over time, which is really important in our process because the time from the start of oxidation to the final product can be over a week in a lab. The effects we selected were time, applied APS per gram, and temperature. This first table are the treatment conditions for our central composite design. In the second table, I have listed here the treatment conditions, the range of conditions that we used during the entire investigation relative to the published work here. And you can see that the range in our work was a little bit broader. And that covers some of the preliminary work we did in order to identify what the right conditions for the central composite design were. As part of the process, we code and relativize the scales prior to analysis. And what the central composite design does is it allows for a quadratic response surface of treatment effects to be produced. Now, if you look at these published data, you'll see that they're fairly more aggressive and a little broader and higher in range. If you recall, I mentioned that the process for ammonium persulfate is not well documented in the literature. And the reason for that is, I guess the best way to describe it is most of the researchers are focused on the finish line. The fiber itself is a raw material for a finished product. And so they tended to focus more on creating CNCs, not so much on the process. So with regards to surface chemistry, the carboxylic acid content that we developed on the surface of our nanofibers was determined by a method called conductometric titration. And what we do is we protonate the sample with a strong acid and titrate against sodium hydroxide. And so during the titration, the first inflection point is our strong acid. The second inflection point is our weak acid. And for ammonium persulfate, we have a very challenging inflection point to measure. And so on the right-hand side, you see this device here. I designed an Arduino-based microtitrator in order to prevent, during the titration, of overshooting that inflection point. In traditional titration, it's very easy to miss that. I do want to make one point about surface chemistry and why I think it's probably the most important characteristic of nanofibers. The surface charge really determines the stability of the colloid formed in the solvent or solution that you've selected. And if the nanofibers aren't designed for that solvent, it really doesn't matter what morphology you achieve, you'll lose all your capability or the contribution that NFC was designed for. Second, it also provides a backbone for further functionalization. So if you're going to take your NFC forward and make it hydrophobic or hydrophilic, or as a transport, this is the methodology that we use. Nanofibers, one point I want to make, cannot be seen by the naked eye. And so in order to determine the diameter and length or the morphology of the fibers, we use a method called atomic force microscopy, and it measures the nanometer topography of samples. AFM has a resolving power that's about 1,000 times greater than an optical microscope. And the way it does this is it detects the deflection in a probe as that probe moves across the surface of our sample, and then generates a three-dimensional topographic image for us. So if you look at this left image, this is a two-dimensional XY plane that is generated in data. And from here, we can derive and generate the length data. In the three-dimensional, the AFM gives us a height number here, and that height is equivalent to our diameters in our fibers. So from that, we can generate a frequency plot of fibers for that particular sample. Crystallinity is the other morphological aspect that's important, and we use X-ray diffraction to measure that. And this test measures the scattering intensity of an X-ray beam from the nanofiber. The diffraction pattern produced here on the right is unique to the material, and from it we can determine the percent crystallinity using the Siegel method. This is the equation here. So what it is it's the difference between the amorphous valley here and the peak of greatest intensity. The other method that I also use is what's called deconvolution, and that's represented by these red peaks here. And that's to determine the crystallite size. And that value, the reason for that is to determine what the theoretical maximum surface charge that we can develop for those specific conditions. So now I'll get into a discussion and summarize my results, starting with surface chemistry. So if you look at surface chemistry, a statistical analysis revealed that the applied concentration of ammonium persulfate had the greatest effect, followed by time and followed by temperature. So if you look at the response surface that was generated on the left here, as you increase applied chemistry or increase time, the surface charge on the surface of the fiber increases accordingly. Holding ammonium persulfate held constant on this right one, same thing, just adjusting temperature and time, you can see how the surface charge responds accordingly. These 3D surfaces allow us to hold one effect constant while evaluating the effect of the other treatments on our response. Applied this same technique to morphology, but if you recall from that first graph that I showed you with the way APS reacts, diameter was strongly affected by time, and it's a very fast hydrolysis reaction. And so in all of the factors, there was no significant difference between each factor in our experiment. Length, however, statistical analysis showed that, again, ammonium persulfate applied had the greatest effect, with temperature close second. Crystallinity, on the other hand, was only affected by temperature, and neither were affected by time. So the 3D surface plot here, again, same thing. We can hold time constant since it's not an effect, increase our applied chemistry, increase temperature, and see what the response is for our length. On the right, XRD diffraction pattern here, holding temperature constant and showing that without temperature moving, we have a constant crystallinity. The patterns as surface charge changed were identical. So the response surface model, as I stated before, allows us to evaluate the effect that each treatment has on fiber response, and that's the effect that's predicted by the model. So in this example, this animation here, I just wanted to show it as holding temperature constant, and I move my cursor across the surface. I can identify the specific treatment conditions for that response, or that predicted response. In my discussion in part 2, I will demonstrate how I can apply response surface methodology to 2 responses in order to determine what the experimental treatment conditions would be. Now, in order to prove the model, it requires a validation step. And so in this case, I picked 3 points. One that landed within the boundaries of the model, as represented by this square plot. And then I picked 2 that were outside the boundaries of the model. And the model predicted that this surface charge would be achieved, and the actual was this. And in all cases, we were within 4% error from the predicted versus the actual. So it really shows that this model has some robustness, contrary to what some research was reported being unrepeatable. So this is good for us. The final thing we did was now to apply the ammonium persulfate oxidation to lignin-containing residuals. And we selected unbleached northern softwood kraft and hot bind. So if you look at this diagram on the left, you can see in the images here, unbleached is a brown color because of the ligand. And as it progresses through time, it becomes whiter and whiter. This chart compares the bleached surface charge that was developed in the central composite design to these ligand containing. And the first thing we noticed was there was a really large downward shift in surface charge development for the unbleached softwood. And that's these two lines here. This is consistent with what we would expect if the proxyl radical was no longer converting aldehyde groups on the carboxylic acids, but being scavenged in competing reactions with lignin. What was interesting, though, is although the hot bind here, you can see that this rate of surface charge development was similar, it didn't have as large a shift. And this is likely due to the more readily oxidizable forms that you see in non-wood and hardwood fibers, specifically syringyl alcohols. And what we think was happening here was the reactions with the syringyl alcohol generated additional carboxylic acid groups. And so as the measured value did not shift nearly as much. Finally, I took a film, or produced a film of the hot bind NFC. But however, due to its really poor drainability, the large number of fibers that required to make the film, it really isn't very feasible. It's great to demonstrate the transparency of the film. You can see the book below the film. So instead of examining films, in part 2, we chose to use an engineered NFC fiber as a reinforcement for paper fibers in this work. So in part 2, I examine the reinforcement of cellulose fibers in a sheet of paper using engineered ammonium persulfate NFC. So I apply the response surface method to engineer fibers with a specific aspect ratio and a specific charge. I then evaluate the influence of charge and aspect ratio on the retention of the nanofibrillary cellulose, the mechanical strength, and the permeability of the resulting papers. I'll again first present the methods and then the results. So using the response surface model, we engineered a low charge, high aspect ratio, and a high charge, low aspect NFCS amendment for papers. So just a comment about paper making. Retention of fine nanoscale materials such as NFC is very problematic in paper making. And so paper makers utilize a retention chemistry in order to capture those nanomaterials and be able to take advantage of their properties. And so to accomplish this in this first step, we take the wood fibers, pre-treat it to adjust the conductivity and the surface charge. And what I used was a chemical polydadmic. And what polydadmic does is it compresses the electrostatic double layer on the surface. And then it allows our cationic polyacrylamide, which is our retention aid, to rather than laying flat on the fiber, to kind of create a net or a web that can capture the nanofibrillary cellulose fibers in this step here. And what that allows is an NFC fiber bridging mechanism between wood fibers and the nanofibrillary cellulose fibers. And this is so just put it in perspective, you saw the film. This is a sheet of reinforced paper with a few coins just for scale. It's about 6 inches in diameter. So my discussion of methods will be focused primarily on application of the RSM method to engineer the fibers. I'll only mention the physical tests in favor of spending a little more time discussing the results. So as I stated before, response surface methodology offers a way for us to adjust, in this case, surface charge and morphology while constraining the treatments. But it also allows us to constrain responses. And so we chose to constrain not only the applied ammonium persulfate on fiber, but when the response is percent crystallinity, and then limit our changes to surface charge and aspect ratio. So if you look at the surfaces here, and we select a point on that surface for the target aspect ratio, we can drop down and identify what treatment conditions are required to achieve that. Same with surface charge. But as you can see, that the 3D surfaces do not present a really good useful tool for performing that analysis. So to provide a better visualization, on the right, I overlaid just the XY data for the RSM model for these plots, selected the point at which both plots intersect. So this is the charge target for the high 1.34, the aspect ratio of 60, and then I can pretty easily from here identify that 80 degrees is the temperature of treatment and 420 minutes is the time. And this is summarized here in this table. Our targets, you can see maintain crystallinity pretty close together. And for the low charge, 70 minutes, and high charge, 180. One thing to note is it is possible to over-constrain the system and not find a solution doing this. So this is a very iterative approach to identify conditions that meet your design criteria. With physical testing, for formation, we use scanning electron microscopy. For strength properties, we use tensile testing. And in order to determine the porosity of the sheet formed, we use permeability. So I'll summarize the results starting with formation. So in this image here on the left, this is a scanning electron microscope image of our paper, of the base paper. And you can see that fairly good formation, but it's fairly open, and not very densified. Looking at the low charge reinforcement, as we increased the addition of NFC at 5%, we can see a measurable and detect a measurable densification of the sheet and a closing up of the pores in the sheet. That increased as we doubled the addition rate. And in this image, you can actually see the edge of the paper. And we confirm this measuring caliper as well of these sheets. Same trend with the higher charge at 5%. Not as much of a closing up the sheet or densification, but same densification. What happened when we doubled the high charge amendment, we got the opposite. And you can see this when we were actually forming the sheets. You can see that the electrostatic repulsion was starting to dominate the formation. There were large flux forming. And if you look at the edge here, you can see that the bulk of the sheet actually increased and got larger. If we increase the magnification and we look at the surface of the sheets, this image shows two fibers actually. This is a pit in the outer wall of one fiber. And you can see going across the surface, these small little kind of shadows of nanofibrillate cellulose. And you can also look at, if you look at the boundary between the overlapping fibers, it's not very discrete, and you can see quite a bit of bridging in it. If you look at the same magnification with the base paper, I try to find one with a pit as well, you can see that there's a very clear delineation between fibers. And so this demonstrates that our retention system managed to capture the NFC fibers sufficiently. Now, our mechanical response for the reinforced paper was measured using a tensile tester. These solid lines in this graph represent the low percent NFC, and the dashed lines are the high percentage of NFC, with green being the low charge and blue being the high charge. So as high charge, low concentration, we observed a large improvement in Young's modulus, about 18.6%. And what that indicates is that the NFC is improving the low carrying capacity of the fibers in the sheet, while simultaneously strengthening and toughening the sheet. And we see the same trend compared to the base tensile here in this right diagram. And as we increase the amendment level of the low, our tensile is increasing. And we've got about 26% increase over the base sheet. Same trend at the low percentage high, toughness of the sheet improved, but then it dropped and we lost all our gains when we started seeing those electrostatic repulsion effects. And at the low charge with tensile, or actually high charge with tensile, we still got a much better improvement for tensile than the base sheet, but not nearly as high as with the low charge. With regards to permeability, I'll say one thing about Air permeability is really a test that's really affected by sheet densification and blocking of the pores by nanofibers. And so what we observed here, again, as with a lower charge fiber and amendment increase, we got a 93% reduction in permeability versus the base sheet, not nearly as strong a reduction with the higher charge. If we look on the right here and compare tensile development with permeability, as we reduce the permeability, we see an increase in tensile. And this confirms that our bonded area was increasing due to the nanofibers present. Finally, I want to bring us back to a comparison of the other two chemical chemistries, sulfuric acid and tempo, and so specifically with regarding to tensile development. So these blocks here represent the tensile development in our samples relative to recently published sulfuric acid and tempo. And I selected papers that use the same retention chemistry that we did. And what you can see is that ammonium persulfate, both surface charges developed a much stronger sheet and matched the reduction in permeability compared to recently published research for sulfuric acid and tempo reinforced papers. So to conclude, the methods that we developed allowed for us to engineer and tune specific fiber characteristics of NFC. It was effective at oxidizing lignin-containing feedstocks. We got an improvement in physical properties that was either equal to or higher than what's been reported in the literature for NFC. And ammonium persulfate produced nanofibrillocellulose is far more affordable to produce and more environmentally attractive than other chemically produced nanofibrillocellulose. Some of the implications for this, and particularly with, say, composites, if you just wanted to change the flexibility of stiffness, the only factor that we may need to change is surface charge. And then the really large implication here, I think, is the barrier properties that NFC offers, particularly as a replacement for oil-based polymers in, say, for example, packaging. And this background shot is one of the films I produced and ran it through a laser printer just to show the transparency of what we produced. So this is a list of some of the publications, and I have filed I started the filing process of a patent back last summer. And these are some of the publications either published or approved for publication or in process. And of course, finally, I'd like to send my appreciation out to a number of people. Mike Roy, president of Roy Farms, and Jim Boyd for funding my research. And they're the folks that supplied the hotline that Rick mentioned. Dr. Gustafson, Dr. Bura, Dr. DiChiara, Dr. Moscal, and my GSR, Dr. Van Bolkenberg, my committee for all the support and guidance they've provided over the last 4 years. Dr. Cooper, who is from the ME department, and all the discussions on how to approach life cycle assessments. I spent a great deal of time at the MAF and in conversations with Dr. Glass about AFM. And then during the pandemic, we were actually kicked out of the MAF. And so I have to thank Dr. Young for doing all the XRD analysis of my samples so I could keep progressing. I'm really pleased to be able to use the titles of many of our graduate students who over the years have enjoyed debating and discussing the different methods and merits. Dr. Sufatelli, Daniele Pascoli, Dr. Weiss, and Dr. Goodman. And as I was building this presentation, I didn't realize how many undergraduate students had gotten pulled in at various times to help develop and test some of our methods. And I kind of regret not putting the years they've graduated, although one of the students is still here with us. Dania Inez, Genelis Triplet, Mazda Hutapea, Kian Shear, who's a senior right now, Gloria Agu, and Chelsea Hansen. And I believe Dania is graduating with her master's degree right now from the University of Washington. And then finally, of course, to my family, my wife Raquel, my daughter and son, Elisa and Adrian, who supported me in my path and endeavors in this. Thank you. Oh, and that's that background image there is an NFC that I actually, recall I talked about functionalization. I functionalized that with a UV visible dye, and it looks transparent in normal light until you add UV. So just kind of demonstration purposes. Thank you.
All right, thank you, Kurt. And why don't you turn off the recording thing?